So I would like to introduce our next speaker, Jesper Møller, the Director of System Architecture at Configit.
I can't hear you guys. Can you hear me?
Yes, we're all good.
Good. Thank you, Tom. So yeah, we have now seen how you can build product models in ACE. And the next thing we're going to look at is how do you validate and verify that a product model works as intended. As we've seen, ACE support different ways of creating product models. You can either author them directly in ACE in the model UI, as Laura just showed. You can import data, so features, rules, and product models from external sources, for example, a PLM system or ERP system. Or you can combine data from different sources and bring them all together in a product model in ACE. And in all these cases, it can be difficult to ensure that the product model that you have created actually works correctly. And this is important because the rules in your product model are, if they're incorrect, you actually risk offering configurations to your customers that you cannot manufacture. You can also risk that certain configurations that you can manufacture will never be offered to your customers. And in both cases, you risk, of course, losing money, getting unhappy customers, and losing market shares to the competitors. So it's important that your CLM solution has good testing and debugging capabilities. In this presentation, we will look at 3 different ways that you can verify that your product model works correctly. And I just need to get this one going. There you go. So first, we'll look at how you can test and debug the behavior of a product model in the debugger in ACE Verify. The next thing we'll look at is how you can verify that the rules in the product model are consistent and don't contradict each other. And this is especially important if you import rules from different sources. And finally, we look at how you can use the solution space to gain insight about your product model, for example, to ensure that the product model is consistent with respect to your bill of materials. So suppose that you're configuring a product and you wonder why you cannot select a certain option, for example, a large battery size for a hearing aid. How can you figure out why? So let's see how you can use the Verify module to help answer that question. So I basically go to the Verify module and I find my product that I like to check. I enter the configuration that I am interested in analyzing. So in this case here, I select a certain type of switch. I select a telecoil, and then I can see there in the middle, the battery size 312 is still available. But when I select the receiver in the ear, this option becomes incompatible or invalid. And now I can use the debugger's explain why feature here to give me a detailed step-by-step explanation of why this combination of selections is not valid with respect to the rules. So I get a list of all the rules that together have the combined effect that I cannot get that battery size that I expected. I can now go back into the model and inspect these rules. So let me do that here in a second. So a moment. There we go. So I basically look at the rules that were explained here in the debugger. And the first rule that I will be interested in looking at is the rule for music streaming. So I'm going to find that here in the list of my rules. When I open up this rule, initially it looks okay. But then when I look closer at it, it basically says something like, if A or B, then A and B. And that looks a little bit suspicious to me. But luckily, I can actually go up and take a look at all the valid combinations that this rule allows. And I can convince myself that this actually looks okay. in this case here. So this rule is fine. And the next rule I'm going to take a look at is a space restriction rule. And this is a slightly more complex rule, as we can see, a lot more going on there. And I can again use this truth table functionality to get an overview of what does this rule actually mean? What are the valid combinations allowed by this single rule here? And I can inspect the different parameters and ensure, convince myself whether or not this rule actually works. So that's a quite useful feature just within the standard modeling tool here. So the next thing we're going to look at is a typical problem that often occurs when you work with creating a product model, and that is, how do you ensure that the rules that you have created in the model are actually consistent? So here's a typical problem. I'm in marketing, and I would like to know whether the rules that I have created are consistent with the engineering rules. Very often, there will be a set of marketing rules that define what product variants you would like to offer in the market, and there'll be a set of engineering rules that define what you can actually build. And it's of course important that these two sets of rules are consistent. Otherwise, you risk promoting some product variants in your sales and marketing material that you cannot engineer and cannot manufacture. So how do you check this? So basically, here is a very simple example that Laura also went through in her presentation. I have defined a rule, a marketing rule, that specifies that the product variant I here invisible, as we can see up there at the top, can be offered with 4 different power levels. Power level 1 being the standard, that little yellow check mark there with an S next to it, and then 3 other power levels that are optional. But how can I be sure that there are no other rules in the product model that will disallow this rule here, or basically disallow the fact that I have tried to express in this rule? So before we go into details with how you actually do this, I would like to talk a little bit about verification and show that verification is actually a pretty cool thing. It's much more powerful than just testing your models. So to begin that little story, back in 1994, Intel launched a new Pentium processor that unfortunately could not divide correctly. They had tested that the processor worked for some combinations, and it did, but they had not tested all possible combinations. And why didn't they do that? Well, obviously because there are a lot of different combinations. In fact, there are 1.8 times 10 to the 19th different combinations that they would have to test. And even if you could check, let's say, 1,000 combinations, 1,000 divisions every nanosecond, it would take you more than like 14 years to check all the different combinations. And that's clearly not feasible. So Intel only tested some of the combinations, and unfortunately, they did not find the error. It ended up costing them a lot of money, as you can see here, several $100 million, because they basically did not test all valid combinations. So luckily for Intel and others, a new research area had started in the late 80s, early 90s, called formal verification. And basically the idea is that you build up a solution space. That's at least one approach in formal verification. You build up a solution space of a model, and then you use this solution space to check all combinations. And you do it in a clever way, so that you don't have to explicitly run through them, but you can actually check a lot of combinations in a very short time, a few seconds or a few minutes, rather than years. A key enabler for this type of verification was the invention of a new data structure called binary decision diagrams, or BDDs. And in fact, BDDs turned out not to just be an interesting data structure, but a key component in verification. it was in 2019, Stanford professor Donald Knuth called BDDs for one of the only really fundamental data structures that had come out the last 25 years. And I guess most of you know who Donald Knuth is, but he's one of the great pioneers in computer science, also a Turing Award winner. And Configit's technology used in ACE and used in the ACE Verify module, virtual tabulation, is based on BDDs. And it is this technology that allows us to perform not just a test that your models work, but actually a formal verification that the product model is consistent. So let's take a look at how that works in action. So I would like to verify now that the marketing rule that we just looked at is consistent. And I can go into the verify module here, and I can see that there are actually two of my options, the power level 3 and 4, that are not available when I look at the entire solution space. And the tool can automatically point me to the rules that are problematic here. So I can see that there are two rules, one relating to the power level and style, and another rule relating to what features are actually available. And I can go now and check that these rules, in fact, do restrict me from getting those two power levels that were not available, as we can see here on the screen. For the specific type of hearing aid with the style ITE, the two power levels at the bottom there are not available. So we can see that here on the slide. This verify module gives me a nice overview of the different rules that are causing this problem with my model. And I can now go and correct the engineering rule if that's the one that's causing the problem. Or I can talk to marketing and say, you cannot get these two options here in your brochures. To introduce the third type of verification, let's look at another typical challenge that you're often faced with when you work with modeling. I'm now an engineer, and I need to engineer a new component, a new piece of hardware, for example, whose design depends on the configuration. For example, it could be a new component of the hearing aid that depends on the type of microphone and the level of so-called spatial sound. So some of the technical things in the hearing aid. Now I can, of course, go and take a look at those two families in my product model, and I can see that for each of them there are three different features that I can select. Directional type of microphone, a dual directional, and omnidirectional. And for the level of spatial sound, there's also three different possibilities. But the question is really, are all these 9 combinations valid? Do I need to engineer 9 different variants of the new component that I'm going to build? Okay, I can, of course, go and take a look at the rules. Here I'm looking at the rules in which the microphone family occurs. I can open up each of these rules and take a look at them and see how they work. They don't look too complicated. If I open up the rules for the other family, the spatial sound, I get 2 other rules. And the challenge is, of course, that each of these rules also talk about other families in my product model. So quickly I end up with having to look at numerous different families and numerous different rules. And that, of course, gets pretty complicated and quite unmanageable. Fortunately, ACE can actually construct the solution space. And let's take a look at how that works. So basically, I open up my model and I select the 2 types of families that I'm interested in here, the microphone family and the spatial sound family. And basically what ACE does now is that it constructs all the combinations of those 2 families that are valid with respect to all the rules in my product model. So it takes all the rules into account, it generates the entire solution space and projects it down to the 2 dimensions here that I'm interested in. And as we can see here, there's actually only 5 combinations that are available. So I only need to take those 5 combinations into account when I have to engineer my new component. So let's take a look at how this solution space actually works. How do you construct it? How can you use it? So in general, if you have a product model with, let's say, n families, then the entire solution space is going to be that n-dimensional space, if you can sort of comprehend that. And that space contains then all the points that are allowed by the rules. So that would be sort of all the solutions that are allowed by the rules in your product model. And typically you have product models with hundreds, maybe even thousands of families and rules. So it quickly becomes quite complicated to analyze how these rules work together. Often you're only interested in, let's say, examining a subset of your solution space, where you basically limit or you project that n-dimensional space onto something smaller, a smaller subspace, with those families that you're interested in analyzing. And ACE can do that very efficiently. It can create the solution space. It does that as part of compiling the product model, and that representation is also used in the Configit API that Jens will talk about later after this presentation here. But as you could say, as a byproduct, we can use this solution space to do that type of analysis that we're interested in. So in this case here, I can zoom in on 2 dimensions in this solution space here, the green and the blue dimension. And ACE can then tell me exactly what are the valid combinations in that entire solution space that are available. And I can see here that those 5 different combinations are the only one allowed. And I can, of course, use this information. This is quite valuable because I can now engineer my product in a way where I only have to support those 5 cases. And in fact, like Henrik also mentioned, it might also turn out that once you generate the solution space, that you realize that there are many more combinations that you probably didn't anticipate. And then, of course, you would have to go back and fix the rules in the product model. Yeah, so to summarize, we've seen 3 different ways, 3 different applications of the verify module in ACE that you can use to ensure that your product models work correctly. We've seen how you can test and debug the rules and get good explanations on why the rules actually behave like they do. We've seen how you can verify formally that the rules that you have created are not in conflict. And we have seen how you can use the solution space to prevent, for example, over-engineering your bill of material, so that you know exactly what parts to consider. There are a couple of other cool things you can do with the solution space that I don't have time to go into now, but we could take another session. If you're interested in that, then please reach out to us. One application that we've seen of our solution space API is that you can actually build product selectors that you can then use in your CPQ solutions. And the idea is that you construct an interactive product selector where the user can select what products are available, and he will then make some selections during that process. And those selections are then given to the solution space API, and then we can further restrict the solution space as part of that process. The solution space is actually, or the API is designed so that you basically ask for how many solutions you want. You basically set a limit on how many solutions you want, and then the API generates those, let's say, first n solutions. And that also means that even though the solution space may contain, let's say, 1 million different combinations, you can still work with the solution space. It can sort of stream the next 100 solutions that you're interested in, and then you can present those to the user. Another application we've seen of the solution space API is that you can use it to verify that your interfaces are correct if you work with multiple product models. So the idea is here that if you work, for example, with system-level configuration in ACE, and you have linked a submodel to a parent model, you can use the solution space. You can construct the solution space for the variables that define that interface between those two models. And then you can actually check whether, for example, the submodel restricts the parent model or whether the parent model restricts the submodel. Because those two solution spaces can then be basically compared, and you can see how what are the valid combinations allowed by each of the two models. And you can use that information to make sure that you actually define that interface between those two components in the correct way. Yeah, so all in all, to conclude this presentation here, the Verify module in ACE and especially the solution space APIs on the ACE platform are extremely powerful verification tools that you can use to analyze your models. So I guess before we move on, if there's any questions.
Excellent. Thank you, Jesper. We did have a question come in, and it asks, can you build or visualize solution space with non-discrete variables? And I would imagine this is asking kind of like variables that have an input range, like a numerical value of some kind.
Yeah, you can do that. Yes, that is possible. I guess there's a couple of different ways that the solution space will then be returned. You can either imagine that you get intervals of equivalent values put into one cell. So you'll have one row that basically represents a range of values. You might also be interested in getting the discrete points out as part of the solution space. But yes, that is certainly possible.
Perfect.
Other questions?
All right. Well, did have one other additional question here that I personally have wondered. What kinds of analysis can you do with the solution space? I'd imagine the API opens up a whole world of possibilities.
Yeah, I mean, I guess you can use it, like Henrik also mentioned, you can use it for many interesting things. I mean, once you get insight into how different variables actually depend on each other, one application of that is, like I mentioned, the over or under engineering of your BOM components. But you can also get into a situation where, for example, if you have a rule that you've defined in your model, and you know that rule makes a certain restriction on your solution space. But if you're not quite sure exactly what combination does it actually rule out, then you can construct a solution space before you create the rule and see what are actually the valid combinations between the variables that I'm using in this rule. And you can use that information to actually ensure that you sort of design the rule in a way that matches that information, right? So you don't sort of put too much logic into the rule because other rules are already covering that scenario. And of course, you can imagine other things are two variables independent of each other. That could also be an interesting thing to look at. And finally, we haven't really talked about that, but of course, since we also deal with time as an aspect here, the models will typically have rules that are driven by effectivity. Then there might be certain points in time where you're interested in how does my solution space actually look here? How does it evolve from one point in time to the next? So you can also use that information to sort of see what valid combinations are available for two different variables over time.
Awesome. All right. We do have two more questions here. I'm going to try to combine them into one because I feel like they're pretty similar. It talks about submodeling and how you can combine several smaller models into a larger one. Is that something you could talk a little bit about, or is that something best saved for another presenter?
Yeah. No, I could do that, definitely. Yeah, it's a little bit outside the scope of verification, you could say, but it's certainly an interesting topic. But yeah, that is a feature in the ACE application that you can work with submodels and parent models. So basically, you can define a product model, and within that product model, you can reference one or more other product models as submodels. And you can make that just a simple association where you say, for example, I'm building a car. the car has one engine, so I'm having one instance of the engine product model as part of my car product model. That could be a very simple scenario. You can also have a whole array of instances. For example, I know the wheels might not be a good example in real life, but you could imagine that the car has 4 instances of the wheel product model, assuming that they were the same type of component, really. So that's what we sort of call a static model. We also do support that you can have dynamic models. So basically, you can specify that, for example, a product has a collection of components, a collection of wheels. If this was a car that you could equip with a range of wheels, for example, and you can put limits on it. Of course, you can say from 0 to 10, or it can also be unbounded. And then basically you define rules that then restrict certain aspects of that dynamic model. For example, what is the maximum let's say power used in all these components summed up together, or maybe that each of the components should have a special type of family set. So you can write these system level rules like that. And it's a quite powerful feature that we introduced in the ACE product quite recently.
Excellent. Thank you so much, Jesper. I really appreciate your time and sharing us with some of those stories. I know myself, the first time I saw solution space, it was something I've never seen in the CPQ landscape before. It's just something that you can't really compare, with Configit.